This is midterm 2013, question 3, part C, which is the food truck location model with different marginal costs. So the model that we covered in class is there are two food trucks. They are choosing locations and choosing prices with the same marginal cost. So the difference here is basically there is a different marginal cost CI for each one of the two food trucks. So the first step is exactly the same. So you write down the profit function here, which is price minus cost multiplied by the quantity demanded. And quantity demanded in the first case is 0, the second case is this, and third case is just 1. And the cases is given by a function or a relation with the other guy's price. So that is exactly the same as the thing given in class, so I'm not repeat that. And the first step is basically calculating the optimal in each case. So the optimal in the first case is basically anything, because no matter what price you choose, as long as price satisfies this condition, then it's always 0. So any price would be the optimal. So that's what I call the upper boundary solution, which is anything in that interval. And the second one in the middle, we need to find the thing, the PI that maximizes this expression. So the idea is first order condition. So take the derivative, set it equals 0, and I call that interior solution. So this is basically the first order condition. And then after you solve the first order condition, setting the derivative equal to 0, and simplify, we get this optimal P, which is one single point. And the thing we need to notice is that for the interior solution, this condition must be satisfied. So we substitute this optimal PI back to this condition to get actually what condition needs to be satisfied for the other guy's price. So then we have some expression like this, which characterize the condition for the interior solution to be the interior solution of the other guy's price. And at last, there is the other boundary, which is this thing. This thing is strictly increasing PI. So the higher the PI, the better. So, and PI is basically bounded by some number, this number here. So the higher the better plus this bound means that this single price is the optimal price. So that's why I get this thing as the lower boundary solution. So what I have now is the optimal price in 3 different intervals of the domain, and they are given by these 3 things. So from now on, I will call this price, this argument that maximizes the profit, the upper boundary solution, the middle one, the interior solution, the last one, the lower boundary solution. So then we calculate the optimal profit according to these 3 optimal prices. And what we did is just substituting these 3 expressions back into the profit function. You get 3 different expressions, 1, 2, and 3. And after simplification, we get these 3. So what these 3 things mean is basically the profit at different parts of the domain at the optimum. So then when 0 is greater than both of these, it means that the upper boundary solution will be chosen as the final optimal. And similarly, if this middle one is greater than both of the other ones, it means that the interior solution will be the solution to the optimization problem. And similar for the other one. But the tricky part of this question is there is a condition for the middle one to actually be an interior solution. So that'll be why we need to combine this condition with what I just said, which one of these 3 is the largest. We combine that thing with this condition to figure out when each one of the solution, so the two boundary solution and the interior solution, is actually the best response. So as I wrote here, the best response is possible to be each one of these three, but the condition is different. And so the hardest step here, that's different from what I covered in the tutorial and what the professor did in class, is that it's very difficult to actually figure out the conditions. So as I said, for the first one to be the first, for the upper boundary solution to be the solution, we need 0 to be greater than both of these two. But the problem is that 0 is never greater than something squared. So the only possible thing for 0 to be the largest one of the three is that this condition, this square condition, must never satisfy. If this is never satisfied, then the interior solution no longer exists. Then if 0 is greater than the last one, then it's okay. So that's why I summarize it into 3 parts. So the first one is 0 must be greater than the profit given by the lower boundary solution, and also the interior solution condition must not satisfy. So it's not the interior, that's the optimal. So combining these, this is one of them, and you need and in between them. So it's either one of these two plus that would give you the upper boundary solution actually being the best response. So then if you simplify them, you can see that there are these three. So the first two will never be compatible because it's smaller than something plus 1 and greater than from the same thing plus 3, so it's never compatible. So this never holds. And if you combine the first one and the last one, you see that something smaller than something plus 1 and the same thing minus 1. If this one holds, the first one automatically holds. So that's why only this one is useful. So that would be why I have here only this condition. So you do the same thing for the second case. So in order for the interior solution to actually be the best response, we need this middle number to be greater than 0 and greater than this. Also, this condition must satisfy. This squared condition must satisfy. So then I wrote the same 3 things. So this one being, this thing is always greater than 0, as I said. It must be greater than the profit from the lower boundary as well. And also that those two conditions must hold. And I will prove a bit later that this thing is always true. So I'll basically do that later. And so the only effective two are these two, and they are compatible and they are not substitutes. So we need to keep both of them. So that's why I just copied back here, being the condition such that the interior solution is the best response. So then what's left is the third one. So the third one, if we go back to use the same logic, for this one to be the best, this one must be greater than the middle one, which is never true. And this one must be greater than 0. So there is one condition, this profit greater than 0, and also this squared thing, must not hold, because this profit is always greater. So that will be the main problem here. So we have basically 4 conditions. As I said, this one is the important one that we always need. And we want this, but as I said, this is never true, so this is not useful for now. And we want this middle one, so the interior solution condition must never hold, which means this interior solution must be smaller than one boundary or greater than the other boundary, which is just the opposite of these two. So then, again, we solve these 3. So using the same logic I say, these two will never hold at the same time, so this one is basically useless. And combining these two, being greater than something plus 3 and the same thing plus 1, this one is the binding one. So if this is true, this automatically is true. So we only need this one. So that'll be why in the last case we only have this condition. So that'll be how I get these 1, 2, 3, 3 conditions, which is the hardest part, I think, of this question of figuring out the best response, which is when is each solution actually the best response. So something I missed is how to show that the interior solution profit is always greater than the lower boundary solution profit. So the way to do this is purely algebra. So if one is greater than the other one, the difference must be greater than zero. Then I expand the left-hand side and then recombine it by completing the squares. So to show something greater than zero, completing the square is usually a good way. So complete the square with p and then complete the square with c as well. We get something squared plus 1, which is always greater than 0. Then we can show that this whole thing is greater than 0. And the solution given in the solution on the professor's website actually combine these two. Mm, because if you look at these two conditions carefully, combining these two would mean that if this number is greater than this number, I will choose this. And I will choose this one otherwise, which is equivalent to just the max of these two things. So you can check it, but they are basically things.